Welcome to 9.7 Taylor Approximations, Day 2. So what we're going to do today is we're going to first start about writing a Mclaren polynomial. Remind us if we can remember what y equals e to the x is as a polynomial. We'll derive and compare another Mclaren polynomial, and then we're really going to focus on Taylor's theorem and this error. Okay, so the first thing I want you to do is I want you to write the Mclaren polynomial for y equals e to the x from memory. So think back to yesterday's video or the previous video. As a reminder, this is the formula for the Mclaren polynomial. Remember, Mclaren is centered at 0. Okay, all right, so pause the video and see how you do, and then come back and we'll check to see what that polynomial for e to the x is. Okay, so did you remember that the polynomial that represents the function e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, so on and so forth, all the way up to x to the n over n factorial. Okay, so it certainly does help to memorize this, and we will talk about the ones that we should have memorized as we get more practice. All right? Okay, so the next example is we want to derive the Mclaren polynomial for y equals e to the 2x. And then we're going to compare it to this guy up above and see how it goes. All right, and see what we notice. Okay, so remember, Mclaren is centered at c equals 0, and we have that formula right up above. Okay, so we're going to create our table, and we're just going to go through, we'll go through the fourth derivative. Okay, so if f of c is e to the 2c, all right, then we're going to evaluate that when c equals 0, and we get 1. The first derivative is 2e to the 2c. Don't forget about that chain rule, and when we derive that at c equals 0, we get 2. And you can kind of see the rest. The second derivative, don't forget that chain rule, and then deriving that at c equals 0, or evaluating that, I should say. Third derivative, evaluated at c equals 0, and then fourth derivative at c equals 0. So there we have our table. So now if we just put that into our formula, so remember up above here, okay, where these values on the right-hand side, there's our constant, that's the coefficient of x squared, x cubed, x to the fourth, etc. We can then go ahead and write the polynomial, okay? So remember, those are all of our coefficients. So we have Pn of x is equal to 1 plus 2x plus 4x squared over 2 factorial plus 8x cubed over 3 factorial, so on and so forth. But what we should notice is these coefficients, we can rewrite all of those, right? We could really say, oh, 4 is 2 squared, 8 is 2 cubed, 16 is 2 to the fourth. So we get this pattern. It's really 2 to the n is our coefficient, x to the n over n factorial. So how do we rewrite this? Well, we can go ahead and say our polynomial Pn of x is equal to 1 plus 2x to the first plus 2x squared over 2 factorial plus 2x cubed over 3 factorial plus 2x to the fourth over 4 factorial, all the way up to 2x to the n over n factorial. So if we compare this, right, what's the difference here? Well, the difference is it's that 2 to the x, or e to the 2x, right? So as we're comparing, notice the difference really between these two, all right? And all we did was we changed that power. So how does it change the equation? So we just noticed that that power is really all that's different here within our polynomial. So as I mentioned, it certainly does help to memorize the polynomial for y equals e to the x, among other ones. And as we get to them, I will say, hey, let's memorize those. In the meantime, let's go ahead and focus more on error. Okay, so in the last video, we talked about Taylor's theorem, and we talked about the error remainder, where the error is equal to the absolute value of the actual minus the estimate, okay? And we could find this estimate by finding this formula here, but now we're going to focus on this max error aspect. Okay, so we're going to go through an example discussing, well, what's the maximum possible error we could have? Okay, so something we have to think about is the remainder, or the error, using n terms is at most the maximum possible next term. So the z value maximizes the derivative and must be between x and c. So we're going to look for this z value here, and we have to look for the n plus 1 derivative, okay? And we're going to go through our maximum error. So if we're kind of going through this, we want to find the maximum possible error when P3 is used to estimate the square root of 4.1. So if it's P3, then we know n equals 3, all right? So then we need to find the fourth derivative at z, okay, the fourth derivative. So last video, we made this table to evaluate the square root of 4.1, okay, and find the error there. So we came up with this table. And remember, we said, oh, c is going to be 3, okay, and we evaluated this. Well, today, since we want to find that maximum error, we need the fourth derivative. So we're just going to finish off this table here, and we're going to evaluate that at c equals 3, okay? So when we do, we're going to get this value here, all right? So now we're going to go over here. So that the remainder, or the error for a degree 3 polynomial, right? We need to look for that fourth derivative at z, okay, when n is 3. So we're just plugging 3 in there, all right? And our c value was 3, okay? So the fourth derivative at z over 4 factorial times 0.1 to the fourth. Okay, so what is z? How do we figure out z? Okay, so z is a value that is between x and c. So remember, c was 3 and x was 3.1. Okay, all right, so as we're looking, and we know we already found the derivative. The fourth derivative is this guy over here. Okay, is this right here. So if we were to graph that, okay, what we would notice is the graph of the fourth derivative is negative. So it's this guy right here. It's negative, but it's increasing. So what we have to do is we have to really look at the absolute value of this, okay? So if we look at the absolute value, that's going to be this right here. So which one of those, where does the maximum value occur? It's going to occur up here, okay? So it's going to occur when z equals 3, all right? When z equals 3 is where we get that maximum. So that's why we wanted to evaluate the fourth derivative at z equals 3. And we got this right here. We kind of already plugged that into our table. All right. So now we can go ahead and use this Lagrange remainder, or this maximum error, to figure out what that maximum error is. So I'm going to move over here. So we've already evaluated the maximum of the fourth derivative, okay, of z, of 3. All right. And then that formula, 1 over 4 factorial times x minus c, which is 0.1 to the fourth power. All right, now remember, we're looking at the absolute value of this, so this negative just goes away. And when we plug this into our calculator, we're going to get this value right here. So if we were trying to evaluate the square root of 4.1 using a third degree polynomial, the maximum possible error we would get is this right here. Okay, now remember, from the previous video, we found that the error was actually this right here, okay, from the previous video, which is less than this maximum. So it makes sense. The error that we actually got in the previous video is less than the maximum possible error. Okay, This is certainly not an easy subject, so we will go over it in class with any questions. Make notes of anything you weren't quite clear about. So we're going to continue with that formula to determine now our next example to find the number of terms needed to estimate e to the 0.1 with error below 0.0001. Okay? So the first thing we want to do is we want to look at this e to the x. Okay? So we want to look at that graph. All right? So what we should notice is our ultimate goal is to find the maximum value of the n plus 1 derivative at z. Okay, so let's just kind of go through what the derivative is. If we're looking at our graph of f of x equals e to the x, we're going to have c is 0 and x is 0.1 because we want e to the 0.1. Okay? All right, so what we should notice is f of c is e to the c. The first derivative is still e to the c. The second derivative will still be e to the c. The nth derivative will still be e to the c. So what's the n plus 1 derivative at z? It'll be e to the z. Okay? So we're still looking at this graph. This graph doesn't change for any of our derivatives. It's always going to be the same graph. So what is z going to be? So if we focus on this graph here, we're comparing c to x. Which value here is going to have our maximum? Well, hopefully you recognize that our maximum is going to occur when x equals 0.1, which is going to be our z value. So we're really going to evaluate e to the 0.1, okay? Because z is going to be 0.1. Remember, z maximizes the derivative, and it is on the interval of x and c, okay? And at the end of the notes today, we'll talk about what's the best way to find our z value. But we look at that derivative graph, and we see where is the maximum value, okay? All right, so now we're going to go over to our formula. So remember that maximum error is less than or equal to the maximum value of that n plus 1 derivative at z at x minus c to the n plus 1 over n plus 1 factorial. Well, the maximum value of that n plus 1 derivative is going to be e to the 0.1. X minus c is 0.1 to the n plus 1 over n plus 1 factorial. And what we want this to be is we want this below that 0.0001. Okay, so now it's just a matter of algebra. So I'm going to divide both sides by e to the 0.1. I can drop the absolute value. These will always be positive. Okay, plugging this portion into my calculator, we get this value. Now it just becomes a trial and error situation. So I'm going to okay, well, when n is 2, what do I get? Well, we get 0.0016 repeating. So I plug n in here and I evaluate that. Well, unfortunately, that is not less than our error. Okay, so I have to go to when n equals 3. When n equals 3, and we evaluate that, throw it onto the calculator, we're going to get this value here. Well, the good news is that is less than what we want our error to be. So I know n has to be 3. So what does that mean for our polynomial? That means the polynomial we are finding is a P3 polynomial, or a third degree polynomial. So how many terms are needed? Because that's what the question is really asking. If it's a third degree polynomial, that means we need 4 terms. Okay? Because we've got the constant, we've got the linear term, the quadratic term, and then the cubic term. So those are 4 terms in total. What we're going to do next is I'm going to show you that this actually is the case. We're just going to go through and check our answer. All right? So as we check our answer, I'm going to zoom to a next page. So I'm going to go through this check kind of quickly, right? We are taking our function e to the x. We rewrote it as a polynomial. Now, we really want to focus on just the third degree polynomial, but remember, this is our polynomial in terms of e to the x, okay? Now, we know that when we're evaluating f of 0 or f prime of 0 or f double prime, etc., we're all going to get the same thing, okay? So the derivative of e to the x is always going to be e to the x, and when we evaluate that at x equals 1, we get 1. So we can write our third degree polynomial and evaluate it at 0.1, all right? And we're going to get 1 plus 0.1 to the first plus 0.1 squared over 2 factorial plus 0.1 cubed over 3 factorial. So this is our P3 portion right here. And this last one, that's just our error term. So remember, that's where we get below 0.0001. Okay? So we just omit that guy. So if we were to plug this into our calculator, we're going to get that e to the x, when we evaluate that with a third degree polynomial, we get this value here. To find the actual, we could just plug e to the 0.1 on our calculator, and this is what we get for the actual value. So just to determine the error, right, the actual, which was this guy here, minus our estimate, which was this guy here, and we take the absolute value of that, we're actually going to get 0.00000425, which in fact is less than that 0.0001 that we wanted to. So we can say we're pretty accurate with what we found in that third example or the fourth example on the previous page. Okay? The last thing I want to talk about is how do we choose that z value? Okay? So there's going to be 3 scenarios here. The first scenario is where our derivative, that nth derivative, is going to be increasing, okay? If it's increasing and we're centered at c and we have our x value, our z will always be this x value because on that interval, that's the highest value, okay? If we're dealing with sine or cosine, so an oscillating function here, then the highest we're ever going to be, it doesn't matter necessarily the interval, we would just say that the highest we're ever going to be is 1 for cosine or sine, all right? So the nth derivative at z is going to be 1. So our term, that maximum value, that coefficient is just 1 times the rest of our formula, x minus c to the n plus 1 over n plus 1 factorial, okay? Now the third scenario is where that nth derivative, the graph is negative, but it's increasing. So it's almost a little deceiving. So what we need to do is we need to look at the absolute value of that graph. So if we look at the absolute value of the graph, it really looks something like this, okay? So by looking at the absolute value, now we can see on this interval from c to x, the maximum value is going to be that c value right there. All right, so whatever c is, that's going to be what our z value is, and we'll evaluate it. Okay, so we'll get more practice with this. If you have any questions, by all means, let me know.